How do inductive and capacitive reactance differ in AC circuits? Imagine a circuit where the flow of electricity faces different kinds of resistance that change depending on how fast the current is moving. That's what we call reactance, and it comes from two main sources: inductors and capacitors. These components oppose the flow of alternating current in unique ways, and understanding how they differ is key to mastering circuit analysis. Inductive reactance is caused by inductors, which are coils of wire. When current flows through an inductor, it creates a magnetic field. If the current tries to change, the magnetic field resists that change, producing a voltage that opposes the current. This is based on Lenz's law. The more the current tries to change, the stronger the opposition. As a result, inductive reactance increases as the frequency of the AC increases. The formula for this is 2 times pi times the frequency times the inductance. So, if you double the frequency, the reactance doubles too. This means at higher frequencies, inductors make it harder for current to pass through. Capacitive reactance comes from capacitors, which store energy in an electric field. When voltage across a capacitor changes, the capacitor charges or discharges to oppose that change. And like inductors, capacitors resist changes in voltage, not current. When the frequency goes up, the capacitor charges and discharges faster, which actually makes it easier for current to flow. The formula for capacitive reactance is 1 divided by 2 pi times the frequency times the capacitance. So, as the frequency increases, capacitive reactance gets smaller. This means at higher frequencies, capacitors allow more current to pass. In terms of phase relationships, in an inductive circuit, the voltage leads the current by 90 degrees. That means the voltage reaches its peak before the current does. In a capacitive circuit, the current leads the voltage by 90 degrees. Here, the current peaks before the voltage. This phase difference affects how power is used and how circuits are designed. When both reactances are present, they can cancel each other out. The total reactance is the difference between the inductive and capacitive reactances. If the inductive reactance is larger, the circuit acts more like an inductor. If the capacitive reactance is larger, it behaves more like a capacitor. This balancing act is important in tuning circuits, filters, and matching impedance. In practical electrical engineering, knowing how reactance works helps in designing circuits that filter signals, correct power factors, and tune resonant circuits. Inductive reactance limits current more at higher frequencies, which is useful in transformers and inductors. Capacitive reactance limits current more at lower frequencies, which is why capacitors are used in coupling and bypassing applications. To sum up, inductive reactance increases with frequency and causes voltage to lead current, while capacitive reactance decreases with frequency and causes current to lead voltage. Their opposite effects are fundamental in shaping how AC circuits behave and are essential knowledge for anyone working with electrical systems.